My name is Ariel Isser. I'm a PhD student at Johns Hopkins University, and I work in Dr. Jonathan Schneck's lab on ways of expanding antigen-specific T cells. And in this case, I worked on a method to optimize the output and throughput of enrichment of rare antigen-specific CD8 T cells for adoptive cellular therapy. So one of the issues with adoptive cellular therapy is that the T cells that are specific to cancer cells and can kill them are very rare. And so our lab has been working on, for the past few years, methods of isolating them and then growing up enough of them to put them back into a patient in order to lead to tumor clearance. So we developed a nanoparticle that's magnetic, that has a protein that binds to very specific T cells, and we can use that to extract those T cells with a magnetic field and then expand them over the course of a week in order to adoptively transfer them back into patients to result in tumor clearance. Now, historically, we've first done a CD8 isolation and then done the enrichment from there. But in this case, we wanted to see, is it possible for us to forego the CD8 isolation and just do a direct enrichment from immune cells? And what we found that was very interesting was that when we forewent the CD8 isolation, we got up to 80% antigen-specific cells after a week of expansion, and 3 times the number of antigen-specific cells. And so after these bizarre results, we wanted to get a better sense of why this was happening. And we hypothesized that our particles, when we incubated them with splenocytes, were binding to a whole swath of other immune cells, non-specifically, that could be aiding in this development of this robust response. And so we profiled which cells were getting enriched, and we found that endogenous antigen-presenting cells, such as B cells, dendritic cells, and macrophages, were enriched when we did the splenocyte enrichment, and also helper T cells were getting enriched. And together, we believed that this was leading to this robust response that we found. So in order to prove this, we attempted to do a similar experiment, but in this case, instead of using splenocytes, we did a pan-T cell isolation, just looking at the whole array of T cells instead of just cytotoxic T cells. And we found that this recapitulated the results that we found from our splenocyte enrichment, that we got up to 80% antigen specificity and 3 times the number of antigen-specific T cells after a week of expansion. And similarly, we found that when we depleted the helper T cell subset, that this reduced our yields from this process. More recently, we hypothesized that perhaps one of the mechanisms at play here was that free peptide was falling off of our particles into solution and leading to endogenous antigen presentation. So in order to test that, we compared washing our particles to unwashed particles at a similar dosage of protein, and we found that simply by washing the particles, we completely abrogated the response that we generally found in our splenocyte enrichment. Now, after developing this method of doing direct enrichment from splenocytes, we found that we were able to adapt this now to a high throughput manner of enriching multiple antigens simultaneously. And we found that at a high enough dosage of particles to cells, we were able to do this on a plate, and that we could batch 3 different antigens, in this case GP100, SLY, and TRP2, and get simultaneous enrichment at similar, if not higher levels, to individual enrichments. And so through this process, we have found a method to do enrichment and expansion of multiple antigen specificities of T cells that can be used for cancer immunotherapy by building up an army of T cells.